Out in the cold, silent expanse far beyond Earth, a machine from another era is still doing the impossible. Built in the 1970s, designed for a mission that should have ended decades ago, Voyager 1 continues to drift deeper into the unknown. But recently, something unexpected happened. Instead of only looking ahead, it turned its attention back, toward the solar system, toward its origin, toward us. What it detected has raised difficult questions. Not because of what we clearly understand, but because of what doesn't quite make sense. This isn't just about distance or endurance. It's about strange data, measurements that don't fully align with what scientists predicted about the space beyond our solar system. For years, models of magnetic fields, charged particles, and cosmic radiation painted a consistent picture of interstellar space. But Voyager's readings suggest that reality might be more complicated. What makes it even more remarkable is the source. This isn't a modern spacecraft with advanced processors. It's a decades-old probe with extremely limited computing power, running on a slowly fading energy supply. And yet, it's still sending signals across billions of miles. The journey began with a rare opportunity, a planetary alignment that allowed the spacecraft to use gravity assists, gaining speed by passing close to giant planets. This clever path extended its mission far beyond what was originally planned. Along the way, it delivered incredible discoveries, capturing detailed observations of massive storms, intricate ring systems, and distant moons. But its most intriguing chapter began when it reached the edge of the Sun's influence. In 2012, Voyager 1 crossed into interstellar space, passing a boundary where the solar wind gives way to the wider galaxy. Scientists expected a clear transition, distinct changes in magnetic direction, particle behavior, and radiation levels. Some of those changes were observed, but others were not as straightforward. For instance, the magnetic field didn't shift as dramatically as expected. Instead, it remained oddly aligned, as though the boundary between regions wasn't as sharp as predicted. This raised the possibility that the edge of our solar system might be more layered or complex than previously thought. Then there were the plasma waves, low-frequency vibrations moving through space. These weren't entirely random. They showed patterns and consistency that hinted at underlying structure. While such waves can be explained by natural processes, their behavior continues to be studied closely. Over time, Voyager also recorded fluctuations in background signals that didn't immediately match known sources. These variations are still being analyzed, and while they may have natural explanations, they highlight how much we still have to learn about interstellar conditions. At one point, the spacecraft's transmissions became briefly irregular. Not completely lost, but inconsistent. Engineers attributed this to aging hardware, understandable for a system operating far beyond its intended lifespan. Eventually, communication stabilized again. During this period, slight adjustments in the spacecraft's orientation were observed. These were subtle and likely linked to normal operational factors, but they allowed Voyager to collect new data from a slightly different perspective. What followed were additional readings showing variations in particle density and energy levels. These changes suggest that the region beyond our solar system is not empty or uniform, but active and dynamic. Voyager also carries something symbolic, the Golden Record. This collection of sounds, music, and images represents humanity's attempt to communicate with whatever might exist beyond Earth. It was never expected to be found anytime soon, if ever. It remains a message cast into the vastness, more about hope than expectation. Meanwhile, its instruments continue detecting tiny particles, cosmic dust moving at high speeds. Some of these readings have surprised scientists due to their frequency and distribution, though research is ongoing to understand their origin. There have also been very small, gradual changes in the spacecraft's path. These can often be explained by known forces such as radiation pressure or interactions with particles, though even minor deviations are carefully studied. Through all of this, one thing has become clear: interstellar space is not as simple as once imagined. It's not just empty silence, it's a region filled with subtle activity, shifting conditions, and complex interactions. Voyager 1 was never meant to serve as a long-term observer of this distant frontier. It was built to explore nearby planets and then continue onward until it fell silent. Yet here it is, decades later, still transmitting, still expanding our understanding. What we're seeing isn't necessarily something mysterious or unnatural, it's something unfamiliar. A reminder that our knowledge of the universe is still incomplete. So what happens next? We continue to listen. We analyze. We question. Because Voyager 1 hasn't delivered final answers, it's opened the door to deeper questions. And whatever lies ahead, it's clear that this journey is far from over. As Voyager 1 continues its slow journey into interstellar space, the questions it raises become more profound. The deeper it travels, the less familiar its surroundings become. What once seemed like empty space is now revealing itself as something far more dynamic, subtle, complex, and still largely unexplored. After the unusual readings and fluctuations, scientists began taking a closer look at long-term patterns in the data. Instead of focusing on isolated anomalies, they started connecting the dots across years of measurements. What they found suggested that the region beyond our solar system is not static. It changes over time, influenced by distant cosmic events and invisible forces moving through the galaxy. One of the key areas of focus became plasma density, the concentration of charged particles in space. Voyager's instruments detected gradual increases and decreases that didn't follow a simple trend. These shifts are now believed to be linked to powerful events occurring far away, such as stellar eruptions or shockwaves traveling across interstellar space. By the time these disturbances reach Voyager, they are faint but still measurable, like echoes of distant activity. Another area of interest is cosmic radiation. Outside the protective bubble of the Sun's influence, Voyager is exposed to higher levels of high-energy particles originating from beyond our solar system. These particles provide valuable clues about the wider galaxy, but their behavior is not entirely predictable. At times, their intensity rises sharply, then drops again without a clear, immediate cause. Researchers believe this could be due to variations in the interstellar magnetic field, an invisible structure that guides the movement of charged particles. However, mapping this field is extremely difficult, especially with data coming from a single spacecraft. Despite these challenges, Voyager 1 continues to act as a kind of deep space probe station, offering a rare, direct sample of an environment no other spacecraft has reached. Back on Earth, engineers face a different challenge: keeping the spacecraft alive. Every year, its power supply weakens slightly. Systems are gradually being shut down to conserve energy, leaving only the most essential instruments running. It's a careful balancing act, extending the mission for as long as possible while accepting that it won't last forever. Communication is another obstacle. Signals from Voyager take more than 20 hours to reach Earth, traveling at the speed of light. By the time a message is received, it's already nearly a day old. Commands sent back take just as long to arrive, meaning real-time control is impossible. Everything must be planned with patience and precision. Even so, the connection remains intact, a steady exchange between Earth and a spacecraft billions of miles away. It's one of the most